Good afternoon, everybody. We come to the second talk, and I see Jesse already connected here. Can you try to project your slides, please?
Yeah, one moment. It's, that is strange.
You can't. Maybe I have to make you co-host. I'm not sure because the others were co-host.
Let me see if this works.
Ah, no, it works, yes.
You can see it? Okay. It just showed up in a different place than I'm used to.
I don't know. This looks well. So Jesse will tell us about collider physics and machine learning, a topic that became more and more interesting over the last years. And I think if you are writing a research statement now and you don't mention machine learning, your chances are slimmer, certainly, than some time ago. So I'm curious what he will tell us. Please, go ahead.
Great. Thanks, Sven. So yeah, I'm talking about collider physics and machine learning in this talk. And I'm as surprised as anyone else that I'm doing this. 4 years ago, I was very skeptical about the role of machine learning in high energy physics, but I've been converted so much so that I'm actually now the director of a new National Science Foundation Institute for Artificial Intelligence and Fundamental Interactions. So we pronounce our acronym IAIFI. And here you see the IAIFI logo, which depending on how you look at it is either a capital A with a lowercase I on top of it, or uppercase F and I next to each other. And really artificial intelligence, fundamental interactions, we see this as kind of flip sides of the same coin. And the goal of our institute is to advance physics knowledge from the smallest building blocks of nature to the largest structures in the universe and galvanize AI research innovation. And I'm really excited to see what our institute does over the next 5 years, and happy to talk with anyone afterwards about ways that you might want to get involved in our activities. So this talk is going to be about collider physics. So of course, here's a beautiful collision event from the LHC collected at the CMS experiment. And I've been starting a lot of my talks with this image for two reasons. One, you see these beautiful pictures of jets, these collimated sprays of particles, which are going to feature prominently in my talk today. But also because this collision of particles is mirrored in a collision that's happening between disciplines. And I kind of started to understand this in 2019, which of course seems like forever ago, but a workshop at the Aspen Center for Physics talking about the interface of theoretical physics for machine learning, and seeing the theoretical high energy physics community collide with the mathematics, statistics, and computer science community has been quite exciting for me. And in my own research, I feel like I've gained new insights into particle physics facilitated by advances in machine learning, where particle physics, of course, has an asterisk because many, many fields of science have been influenced by machine learning. And then putting machine learning with an asterisk because it's not only just machine learning, deep learning, it's a whole toolkit from mathematics, statistics, and computer science. And I'll be telling you about some of those tools in this talk today. And by the way, I think with this new institute, we have a chance of also going the other direction, gaining new insights into machine learning using techniques from particle physics. So my talk's going to be organized around two anecdotes from my own research, and I'll try to explain what these images are through the course of this talk. But on the left-hand side is a representation of what a machine has learned. And I'll try to tell you a little bit more about what the machine learning task is. But this psychedelic image turns out to be related to the singularity structure of QCD. And so I'll show you what it means to kind of teach a machine to think like a physicist, and then see what kind of lessons the machine was able to learn armed with that physics knowledge. And then the second anecdote is going to be about letting collider data speak for itself. So in machine learning language, this would be an unsupervised machine learning strategy. And I'll try to inspire some of you who may be not in particle physics about a whole other toolkit that's available that is under the broader artificial intelligence label, but maybe is less familiar to the machine learning community, though nevertheless very important there. But in both of these anecdotes, we're going to be talking about data analysis strategies motivated by the symmetries and structures of particle physics. And as a theorist, what satisfies me a lot about these anecdotes is that behind the scenes, there are these core elements of quantum field theory. In particular, that psychedelic image is exploiting a core prediction of quantum chromodynamics. And the unsupervised learning strategies turn out to be related to understanding nested singularities of gauge theories. So I'm happy to tell you a little bit more about this. I'll try to keep kind of a high level perspective in this talk today. But in both of these cases, we're gaining new perspectives on key theoretical concepts from this machine learning lens. So in the rest of this talk, here's the outline. So first, talk a little bit more generally about machine learning in high energy physics, and then focus on these two examples from my research. And these two examples are connected to relatively simple questions. What is a collider event? Like, what is the data structure underlying collider physics? And in the second anecdote, when are collider events similar? Can you geometrize the notion of similarity? And so hopefully you'll find these examples interesting. And let me just apologize in advance that these examples are, again, drawn heavily from my own research program. And there's a huge amount of work going on in the machine learning community, including by some people I see in the audience. And happy to talk about those things as well. But I focused on my research, well, mostly because these are the things that I'm most familiar with and have been giving a lot of talks on recently. And speaking of giving a lot of talks recently, I have found it beneficial to actually take questions during the talk, just to make sure we're all kind of on the same page. So I'll have these various pause slides. So please interrupt me or drop a question in the chat, and I'll try to answer questions as I go. Some of the concepts I'll be talking about will be new and unfamiliar, and it would be fun to try to explain them in real time. But of course, happy to answer questions at the end as well, if you'd prefer. So let me just pause right now. I assume there's no questions at the moment.
Let me just add, I'm monitoring the participants. If anybody raises his hand, I'll see it, and then you can also speak up. Yeah, so there's no excuse.
Perfect. Great. Thanks so much. Okay, so let's talk about the rise of the machine. So if I want to be a little bit tongue-in-cheek about this, you can ask the question, can we teach a machine to think like a physicist? This actually is an interesting contrast, because oftentimes when we talk about artificial intelligence, we talk about teaching a machine to think like a toddler, like a child, and the kind of creativity and connections that children are able to build. But of course, I have an 8-year-old son, and trying to reason with him is not so easy. And I'd prefer to reason like a physicist, that is, incorporate knowledge from our domain, incorporate ways of checking that the answer that we get is the correct one. And the time-tested strategies of physical reasoning, it would be wonderful to embed those into machine learning technologies. This idea was picked up in the US press. There was an article by Dennis Overby in November with a more provocative title saying, "Can a computer devise a theory of everything?" I don't think that theoretical physicists are going to be out of a job anytime soon, but it is interesting to think about what would it mean for a computer to be able to write down equations, maybe using some kind of symbolic manipulation strategy, and what would it mean for us to be able to understand what the machine has learned? And can we, again, incorporate domain knowledge from physics into our machine learning architectures? And hopefully this talk will give you at least some examples pointing in that direction. Now, I should mention that machine learning has been used in high energy physics for a very long time, especially in the experimental domain. And this is a review that's outdated, even though it was only from 2018, showing some extensive uses of machine learning and high energy physics on the experimental side. From calibration to new physics searches, object identification in neutrino physics, and object classification also in neutrino physics, and many other examples of machine learning kind of advancing physics research. And we all understand that machine learning is transforming many aspects of society, including the way that we do approach the physical sciences. But at least as of 2018, though things have been changing over the intervening time, I would say that a lot of the progress in machine learning and high energy physics has been using off-the-shelf tools. And these are exciting and powerful tools coming from the broader machine learning community. But for example, if I'm looking at the way that neutrino reconstruction is being done in liquid argon time projection chambers, it's often using convolutional neural networks, which come from the 2D image processing world. And this is good for systems that are built out of like fixed grid calorimeters, where you really have a notion of pixels, but less ideal for things like tracking detectors, or when you have sparse data, where the data set doesn't really conform to the assumptions made in convolutional neural networks. There's been enormous progress in natural language processing, and particle physics can fit into a natural language processing framework by using things like jet clustering algorithms to yield semantic structure. But intrinsically, by quantum mechanics, identical particles have no intrinsic ordering. There isn't a natural ordering that you get. And so some natural language processing strategies don't quite fit with what we want to do in the particle physics realm. 3D object data processing is actually much closer to what we do in particle physics, though it doesn't necessarily capture all the symmetries, at least with off-the-shelf tools. And one of the big innovations that's been happening in particle physics has been the use of graph neural networks and in graph-based tools, because graphs actually turn out to map a little bit better onto the type of problems we encounter in particle physics. But this mismatch between off-the-shelf tools and what we want to do in the particle physics context was one of the motivations for this new AI institute that I'm directing, and trying to build what we're calling ab initio artificial intelligence, machine learning that incorporates first principles, best practices, and domain knowledge from fundamental physics. And some of these are ones that the machine learning community is already engaged with. For example, embedding symmetries into machine learning architectures. And I'll be talking about one example of that today. But there's many other concepts that we have, especially in theoretical physics, that you'd like to know, how would you incorporate that into a machine learning strategy? For example, guarantees that your results are exact, or guarantees that your results are reproducible up to uncertainties, or even higher concepts like locality, causality, unitarity. How would you bake those into your machine learning work? And when I was first thinking about this, how would you teach a machine to think like a physicist? I originally thought it was kind of hopeless. And part of what changed my mind was seeing the evolution in the machine learning world for various strategies that I thought of as being kind of brute force, but then I realized that actually domain knowledge in the more computer science world was actually being used in advanced deep learning strategies. So let me show you an example that helped change my mind. So here is a classic image processing task called inpainting, where you have an image on the left-hand side where you have various parts of that image that have been masked. And what you're trying to do is you're trying to predict what's underneath that mask. And you're using basically the prior from having seen many, many, many images to say, if I've seen 1 billion libraries, I've seen them all, and I can figure out how to use that prior to fill in gaps in the image. And the kind of standard lore that I'd heard is that it's the increased computational power that we have, especially with the rise of graphics processing units for machine learning applications and large data sets, huge image databases. Like that was what was driving the progress. But this paper from 2018 is actually not really relying on these two things. This is a case where you have a neural network that's actually never seen any images whatsoever. Rather, it's a randomly initialized neural network. It's never seen any specific images, but the network architecture itself captured the idea that images often have repeating patterns, and you're able to encode that domain knowledge about repeated patterns and understanding the structure of your problem in order to, even without any training, figure out how to do this in-painting task. And seeing this example, so what I'm calling like deep learning meets deep thinking, that you think about the structure of your problem, you're not just relying on the computer and its brute force computational power. That's what started to change my mind about what we could do, and in particular, what ideas do I have that I can embed into a machine learning strategy. So thinking about this kind of at a high level, so if I think about like machine learning targets for collider theory, so if I'm doing a theory calculation, it almost always uses one of these elements of this master formula. Of course, at the end of the day, we care about calculating and interpreting cross sections. But the way we get these cross section predictions is by doing integrals over phase space of scattering amplitude squareds. And there's a lot of people thinking about what are the best observables to make either new physics or old physics, for that matter, more apparent in collider data. And in each of these categories, there's been exciting progress on multiple fronts from the theory community and also from the experimental community, who's even been thinking about how machine learning strategies that have been used in experimental context might be relevant for theory analyses. And again, apologies that in this talk I'm going to be focusing on my research group. I'll make these slides available, and this link down here is to an extensive bibliography of people attacking many of these problems here. But let me give you an example of types of things that are happening in these various spheres. So when it comes to interpreting cross-sections, there's been a lot of interesting strategies about how you can infer parameters of a model, for example, parameters of an effective field theory, with the aid of machine learning strategies. For doing cross-section calculations and integrals, ideas of using normalizing flows to more efficiently do numerical integration. In terms of amplitudes, there's been some interesting work on symbolic regression, where you have numerical information about an equation. You try to learn the analytic structure of that equation. And then in terms of observables, a huge amount of effort going into, well, my field of understanding jet physics, but jet classification, in particular saying whether a particular collimated spray of particles is coming from a quark or a gluon or a boosted top quark or a boosted Higgs boson. So these are examples of machine learning that are showing up. And a lot of this progress, again, has been driven by theorists. So for those of you who have not thought about machine learning and are interested in getting involved, in addition to this idea that I can incorporate my domain knowledge into a machine learning architecture, another thing that changed my mind was to realize that some of the techniques one needs to do to think about machine learning is actually quite familiar to a theorist. And let me give you an example of just something very, very simple that if you've never seen it before, can just help get your mind in the right mindset. For appreciating why machine learning is not just I have a black box and I let it go and the machine makes decisions without my input. Let me show you some of the kind of statistical foundations of machine learning that help me understand why incorporating this into my research was a good idea. So here's a very well-known task that's known as the likelihood ratio trick, and this is a key example of what folks like Kyle Kramer and friends call simulation-based inference, cases where you're trying to make conclusions from sampled data sets. And sampled data sets, Monte Carlo data sets, are something that we do all the time in particle physics. And it turns out that many high-energy physics problems can actually be expressed in terms of this likelihood ratio trick. So let me just go through this as an example. So let's say my goal in life is to estimate the likelihood ratio. I have the likelihood ratio of P of X divided by Q of X. That is the probability of seeing X in one sample P and the probability of seeing X in a different sample Q. But what I'm given is I'm giving just finite samples of P and Q. So, let's say I have, 1,000 events of type P and 1,000 events of type Q, and I want to estimate the ratio of P of X over Q of X. And that's my training data. That's what I'm going to hand to the machine. And then I'm going to have a learnable function that is a function that has a bunch of knobs that it can be turned. F of X parameterized by, for example, neural networks, but there's other parameterizations that one could use. And then I define this loss function or loss functional, which says, okay, I'm going to say success is if this capital L is as low as possible. And my measure of success is taking the logarithm of F over the sample P and the logarithm of an expectation value of F minus 1 over the sample Q. And apologies that I seem to have reversed my color coding of P and Q in this slide. It turns out that asymptotically, you can show that the minimum value of L is achieved precisely when F is equal to the likelihood ratio, P over Q. And in fact, the value of L is related to a statistical divergence called the KL divergence. Okay, and so this is a strategy that if you're given training samples P and Q, you can apply this trick, apply this loss function. There's many other loss functions that can accomplish the same thing. And if you can minimize this L, then you've succeeded at learning this ratio. And as I'll show in a moment, there's many problems that can take this form. Now, this seems at first glance to be kind of a statistics-y thing. But all I'm really doing is I'm doing functional minimization. And this is just the same structure as Lagrangian mechanics, where I have an action and a Lagrangian, I use the Euler-Lagrange equations to find the solution. And phrased in this language, saying, oh, wait, I know what I need to do. I need to have my physics problem. I need to translate it into a Lagrangian language whose optimum, so we usually do extrema in Lagrangian mechanics, but here it has to be a minimum. Its minimum gives me something of interest, either for the value of L or for the or for this final solution. And what this requires is a shift of our theoretical focus to solving problems, to specifying the problems. But if I can specify the problem in the form of a Lagrangian or a loss function, then I can just let the machine do what it does best, which is numerically find the minimum there. And that numerical minimum is often one that is quite useful. So, there is a sense in which machine learning is a black box and that I don't know much about how this minimization is happening. But at least asymptotically, the goal is just to do what we, again, do with Lagrangian mechanics only in a numerical way, is finding extrema of functions where those extrema have some interesting physical value. So just to give you an example of the power of this idea, let me show you from my own work doing something that doesn't seem very theoretical at all, which is detector unfolding. But we introduced a detector unfolding strategy that's based on just likelihood ratios. So we call our method omnifold, and this is multidimensional unbinned detector corrections via iterative binary classification. So this likelihood ratio trick is related to the binary classification problem of whether I have P or Q, given some example data set. And here, what we're trying to do is we're trying to correct simulated data to make it look like the real data, and thereby infer from the truth level information in that simulation what the particle level truth is. So this is the detector unfolding problem. And there's a way of solving this just by basically doing repeated ratios and just using machine learning to compute likelihood ratios and basically correcting your data in an iterative way using these likelihood ratios, such that once data matches the simulation, then you can use your simulation to back out what the truth is. And so this is a well-defined problem. It turns out that you can show that this iterative technique is related to maximum likelihood strategies. And we've been playing around with this and doing things like this, like going to archival data from IAIFI, where they measured quantities involving jets, in particular this quantity called thrust. And we can go to archival data shown in green, where the way that archives are normally stored is by histogram bins. And you can see these histogram bins in green have varying sizes. Why? Because I'm trying to plot something in logarithmic space, because as a theorist, I'm actually interested more in the logarithm of thrust than thrust itself. Oh, but shoot, they have this one giant bin that because we stored our data in a bin form, I can't back out. But using this omnifold technique, we've actually gone back to IAIFI archival data. And even though what's shown here in red is binned, it's actually, you can use this machine learning flexibility to actually make an unbinned unfolding, where you just basically correct your simulation via this likelihood ratio, and you get per event weights that then you can use to fill histograms later. And then this allows us, for example, to revisit this the small 1 minus thrust region, where actually it's interesting from a theory perspective. So this is a case where we're motivated by a theory issue, but we have an experimental benefit, but it comes again from this theoretical underpinnings of finding a good loss function to address the task at hand. Okay, so this is a good time, I think, to pause. So, should we be worried about the rise of machines? No, I think we should be excited about the rise of the machines. If we can translate our high energy physics problems into a language of optimization, we can capitalize on the deep learning revolution. And this is interesting to think about from a theory perspective of like, what are the theory questions that I have that I can actually phrase in the context of minimizing a loss? Are there problems that would benefit from this perspective? Okay, so let me pause here, ending the first chapter of this talk, see if people have questions about this before I move on to 2 examples from my research.
No raised hands so far. People on Zoom tend to be shy.
Shy. Okay. Well, I will leave this slide up for just a little bit longer, and I'd encourage you in the if you don't want to ask a question now, in the next pause, feel free to weigh in. As you can tell, I'm an evangelist for machine learning now. So I also welcome you pushing back and saying, I've gone off the deep end and okay. So well, let's see if more questions come up in the next part of the talk. So let's now go back to basics and ask the question, what is a collider event? Like, what is it kind of intrinsically as a data structure? And let's, again, put this kind of theoretical lens on. And, we have beautiful collision events like this happening every 25 nanoseconds. We need to infer what's going on in these collisions in quick and robust ways. And of course, there's an experimental challenge of how do you go from the various tracking and calorimeter elements to the actual particles that are being produced. And then once you figure out what particles are being produced, there's the theoretical challenge of then how do you infer from the patterns of those particles what the underlying process might be happening at short distances. But as an intrinsic data structure, if I ignore things like displaced vertices, all we have is a collection of points in momentum space. From each particle going out from the collision point, it's just saying, here's my momentum in the X, Y, and Z direction, as well as its mass. Maybe you have some particle identification information, but basically I just have a collection of points in space. And in the machine learning world, this is well studied. Collections of points in space, not momentum space, but position space, is called a point cloud. And point cloud learning is something that happens all the time in the machine learning world. So here's an example of self-driving cars where we have LiDAR point detectors that are scanning a scene. And you're trying to then infer from this collection of points, what's going around in the scene around you. And there's many similarities between the tasks that you might want to do for a self-driving car and the tasks you might want to do in collider physics. So for example, here we have object identification. These square boxes are identifying interesting clusters for further study. And we have that, of course, in particle physics, where these cones here, these collimated sprays of particles, are these jets, and jet clustering algorithms, jet finding algorithms, are a key task that we do with collider data, what a machine learning person would call a segmentation task. We also want to do object identification. So we want to know whether these jets are coming from a quark or a gluon or a more exotic object. Well, that classification task is one that we do in the machine learning world, of course, all the time. We want to know whether this is a bicycle or a car or a pedestrian. So there's many similarities between the problems that are faced in machine learning in society and the ones that we face in collider physics. But we have an advantage in the collider physics case that we actually know a lot about the underlying structure of our problem, and we'd like to be able to embed that knowledge into our machine learning architectures. So what's something that we know from collider physics that can help us in designing better machine learning architectures? So let me just remind you, again, I'm going to be focusing on jets in this talk since that's my research focus. Jets are formed in the following way. At short distances, we produce high energy quarks and gluons from high energy scattering. Those quarks and gluons radiate and shower additional quarks and gluons via a parton shower process. Those quarks and gluons combine to form composite hadrons like pions and kaons, who that then hit our detector, and that's the information that's recorded. From a theoretical perspective, this is a complicated process that's made simpler if we don't try to tackle the complicated non-perturbative dynamics of QCD. And one way that you can be minimally sensitive to that non-perturbative dynamics is if you focus not on the flavor and charge of the composite hadrons going into your detector, but focus just on the flow of energy. So if I think about the way that I do calculations in theory, in particular if I'm doing calculations in perturbative quantum field theory, what I'm really measuring is I'm measuring the flow of energy from the collision point off to infinity. This is a well-defined quantum mechanical operator. It takes the stress energy tensor T mu nu. The zero component is energy. The I component is the flow. And if I follow that flow from the collision point off to infinity, that's actually the information that we tend to actually be computing when we're doing perturbative quantum field theory calculations, or at least perturbative QCD calculations. This energy flow is robust to hadronization and detector effects. It's well defined for massive, so let's just say massless gauge theory, sorry about that. Well defined for massless gauge theories. And it's been something that's been studied over the years. And I want to raise this to prominence in our machine learning context. So I said this has been studied for many years. The first context that I'm aware of this is from the 1970s, work on so-called energy-energy correlators, where you take two idealized theorist detectors and you pull them apart by angle and basically ask, is there a correlation when one cell fires versus another cell fires? There's a long history in probing the collinear dynamics of QCD using these energy-energy correlators. And here I'm just showing archival data showing that in this extreme collinear regime, there's theoretical challenges with understanding the small angle collinear limit that actually affect our ability to extract fundamental constants like alpha S. Just as an aside, this has nothing to do with machine learning. We were interested in studying these energy-energy correlators, and in some forthcoming work with Patrick Kamitsky and Ian Molt, we've actually made that same plot, but now in jet data from the LHC using public collider data from the CMS experiment. And so here's showing basically if I have these two detectors and I bring them close together, if I bring them close together, is it more likely that one detector fires if the other one did as well? And you see this spike here, which corresponds to the collinear singularity structure of QCD. And you can ask yourself, are we learning something about the small angle limit of QCD? It's a fun thing to plot, but what have I actually learned from this? And one of the things that we learned is that linear plots are not so instructive for seeing the collinear dynamics. But if we go to log space, you see something that's been hiding in QCD data, though just by changing your axes that now become highlighted in kind of a fascinating way, where actually as a function of angle, At large angles, you get perturbative behavior, which gives you this kind of flat behavior in this energy-energy correlator. And then you hit an angle corresponding to lambda QCD, and you see this interesting phase transition, where you're transitioning from a partonic phase that has collinear singularities and self-similarity and running coupling to a hadronic phase where essentially you have a random gas of pions and kaons, which actually gives rise to this interesting EEC behavior and a slope actually predicted by this kind of random hadron gas model. And so this is just saying you can use public data to explore old problems in new ways. And I'll show you this again in a machine learning context a little bit later on in this talk. But here's just a fun use of energy-energy correlators, not from the machine learning perspective. From the machine learning perspective, if we want to take this energy-energy correlator or energy flow picture seriously, we have to figure out how do we translate this theory concept into something that's relevant for machine learning architectures. And the language that we want to use is this point cloud language. And what energy flow is from this point cloud language is weighted point clouds. That is, clouds where there's some notion of weight, where if you have zero weight, then that point is not relevant. Or if you have two objects pointing in the same direction, that's equivalent to having one object where you put the weights together. So this is energy weighted directions. So I'm suppressing charge information, suppressing flavor information, because from a perturbative field theory perspective, those are infrared and collinear unsafe quantities. And if I have energy flowing off to infinity in a particular direction, these energy weighted directions, I can build a machine learning architecture around these weighted point clouds. As an alternate visualization that will be relevant for the last part of my talk, you could also talk about densities of energy. So here I'm taking like a picture, staring down a jet and looking at the particles hitting that detector. And then I can draw dots whose size is the amount of energy that hits there, or for the aficionados, the amount of transverse momentum that hits there. And then where it hits an angle is the location. You can think about this as like an idealized calorimeter that has infinite angular resolution, but still can only measure energy. This is the information that I can both compute perturbatively related to this energy flow picture, but also one that I can build a machine learning architecture around this weighted point cloud concept. So as promised, with these ingredients, we can now try to think like a physicist, okay? The collision of the high energy physics perspective, the machine learning perspective. From the machine learning perspective, what do you need? You need a properly specified problem. In this case, specify a loss function. The example I'm going to show in a moment is involving a classification task. Is it from one category or another, which is related to this likelihood ratio trick I told you before. We have many labeled examples, examples where this problem has already been solved, either in real data or in synthetic data. And then the solution out pops, a function. This is like solving the Euler-Lagrange equations in order to find the solution to your equations of motion. But the solution is one that's going to solve some task of interest to you. So this is all the machine learning. This is what machine learning guarantees you. What we now get from the high energy physics side is we get things like symmetries. The fact that from quantum mechanics, identical particles are indistinguishable. Therefore, when these four vectors come out, their order doesn't matter. This is the same symmetry as a point cloud. When I do LiDAR point detection for self-driving cars, the order of those points don't have any meaning. And then this principle of infrared and collinear safety, which I can encode by having this energy weighting. And this, again, makes sure that I focus on the energy flow and not on things that are ill-defined in massless gauge theories. So I can put these two ingredients together. And as a bonus, I get something that, as a physicist, makes me very happy. I have a way of verifying that the machine has done the right thing. So I'll show you what that looks like in a second. And anytime we can check that the answer is physically sensible, that gives us more confidence in what the machine is doing. Okay, so what does it look like when I put these things together? Well, it looks like this work I've done with my students, Patrick Kamitsky and Eric Metodiev, called Energy Flow Networks. And this is an architecture designed around symmetries and interpretability. And even though behind the scenes there's neural networks, I'm not going to draw any neural network diagrams in this talk, because in some sense, that's not the point. Yes, there's neural networks, multi-layer feed neural networks, and I can tell you how many nodes and things there are. But that's not the point. The point is encoding the structure of our problem. And we've encoded the structure of our problem with this permutation invariance here by having a sum in the so-called latent space. So I've divided my solution into these V functions, a number of V functions that have this permutation symmetry encoded by this sum. I have this linear energy weighting. That means I'm focusing on the energy flow. And it turns out, taking advantage of some work that was done by computer scientists at Carnegie Mellon, that you can actually prove that this functional form, in the limit that this latent space L goes to infinity, and you have infinitely expressive neural networks, actually can describe any infrared and collinear safe observable. And it turns out to be really good for a variety of tasks, including jet classification, which is the one that I'm going to show you in a moment. But what's really nice is that this structure of taking my problem, breaking it down into pieces, and each of those pieces has a relatively simple form. I can then look at those pieces and ask, hey, did the machine learn the right thing? And for this latent space dimension L, I have L functions that I can plot. And these are relatively easy to plot. And as I'll show, basically, this is going to tell you where the machine is paying attention. So there's this flow of energy from the collision point out. And then I'm going to ask, how does the machine organize its knowledge about where in energy flow space it's paying attention to? And then hopefully the machine is making a smart choice about where it's deciding to put its attention, so that I can get confidence that it's putting its attention in places that are relevant for solving the problem at hand. And this gives rise to these psychedelic visualizations that I advertised before. So what are you seeing here? So the jet is going into the center part of this picture. You can imagine a flow of energy going in here, and these rings, you should be thinking of those rings as enclosing an area of focus. So think about these rings as being filled in, and you can see that the machine pays attention to this energy in this little ring or this larger ring, or going out to the periphery, paying attention to kind of big blobs on the outside. And as I increase the size of this latent dimension, I can basically get a sense of, as I hand the machine more ability to be expressive, where does it pay attention to? Here, this is specifically for the case of quark-gluon classification. So for the task of telling the difference between a quark jet and a gluon jet, where is it putting its attention? As I increase the size of the latent dimension, these images get more and more psychedelic. And kind of, if you look at this largest latent dimension size, 256, you realize that there's like this self-similarity kind of fractal structure going in. The machine is paying more attention to the center in smaller pixels, and at wider angles, it's paying attention to things in a more coarse way. And what's kind of interesting is that this pattern is not just a random pattern. The machine, we taught it about infrared and collinear safety. We taught it about permutation invariance from quantum mechanics. And it learned for itself, in some sense, the collinear singularity structure of QCD. It learned that it should pay attention to information on a plot of the radial distance from the jet center and the kind of pixel size. It has to follow a particular power law. And that power law is one that we actually get from the so-called Altarelli-Parisi splitting functions, and the collinear singularity structure, this logarithmic structure in angle. That's what the machine has effectively learned. And that turns out to be, for quark-gluon discrimination, exactly the thing that you're supposed to do, because the radiation pattern of gluons follows exactly that same pattern. So essentially, the machine has learned that if I want to tell the difference between a quark jet and a gluon jet, the way I should pay attention is to information such that I have equal partitioning of information as per the Altarelli-Parisi splitting function. Okay, so this gives you kind of a sense of one arc of logic. So, what is a collider event? A collider event is this calorimeter energy density, at least if I want to focus on this energy flow picture. And hopefully I've given you some evidence that this should inspire set-based machine learning architectures. Set-based because the order of the particles doesn't matter. And then the next kind of leap from set-based, if I wanted to look at pairwise correlations, would be graph-based ML architectures, which I'm not talking about here. But part of the reason why graph-based techniques are becoming more popular is because they can encode the kind of information that you get not just from single energy deposits, but these energy-energy correlators. And that's an exciting direction to be paying attention to in the theoretical world over the coming year. Okay, so let me pause here and see if there's any questions about this part of the talk. Again, taking a physics principle, how do you encode it into a machine learning architecture?
Hi, I have a question.
Yes.
So in this example that you showed with the jets, so traditional ways to detect the jets, so I'm not working on collider physics, so I don't know if this is a naive question. So traditional ways to detect and determine the jets, are they better or worse than the machine learning approach you have? So what is the advantage of the machine learning in this case? Because at least to me, it wasn't very clear.
Good. So I didn't plot show a performance plot, and I may have actually forgotten to put the performance plot in my backup slides. I put something that's relevant for it. So there are two different tasks that we could talk about with jet physics. One is identifying jets and figuring out what clusters are relevant. And there has been relatively little machine learning work. There is some, but it hasn't shown a real advantage. The place where you'd seen a real advantage has been in classification tasks, where you say, I have a spray of particles and I want to know where it came from. So for example, if I have some new physics scenario that generates a lot of top quarks, if those top quarks have a lot of transverse momentum, those top quarks can form narrow jet-like objects. But because the top quark has a characteristic three-prong decay, those jets have three-prong substructure. And machine learning has bested techniques, for example, that I've developed for looking for these boosted top quarks, and kind of bested it by an order of magnitude or more in performance, depending on what you set as your benchmark. So for those tasks, machine learning has kind of dramatically changed our ability to do classification, such that it's much better than traditional techniques, with the caveat that machine learning brings in a whole new set of challenges for how you actually calibrate those techniques. So a lot of traditional techniques are still being used right now as the community figures out how do we best ensure that the use of machine learning is robust. From a theory perspective, I would say that the machine just completely showed me up. So this is going to my backup slides. So here is the same energy flow network thing, but instead of making a psychedelic image with many, many rings, let me make an image that's showing where the machine pays attention to if I only allow it to look in kind of two patches, so a latent dimension size of 2. And so you can see what the machine decides to do if it only is able to look at like basically two filters, if you want to call it that way. It looks at the center core of the jet and it looks at the periphery of the jet, which makes sense. There's soft and collinear singularities in QCD. So this blue one captures the collinear behavior. This red one captures the soft behavior. And here's the actual radial profile of where the machine is paying attention to. So this makes sense, except for that's not what the theorists were doing. What the theorists were doing was, including myself, was thinking about quark-gluon discrimination, not with this kind of Gaussian shape or this logarithmic shape, but with polynomials. And polynomials is a really bad way of capturing the difference between quark jets and gluon jets. And so this is a plot that's showing a performance of how well I can identify a quark and reject a gluon. And these dash curves correspond to the work that I and others had been doing in terms of thinking about this problem in terms of looking at moments of distributions. And you see that it saturates at a point where, you know, it's not the best performance. The machine, this energy flow network, is this green curve. And even though I limited it, what it was able to do, is able to do significantly better on this quark-gluon task. And it does even better if I give it more freedom to learn beyond just these two latent dimensions. And then what we were able to do is take this energy flow network and reverse engineer it, and then come up with a closed form expression for basically, going back to the slide, basically what this blue and red curves are really looking like. A closed form expression that then you can imagine doing theory calculations with. And we were able to more or less match the performance of the machine. So the machine taught us something that we didn't know. And I feel embarrassed for not knowing it, because in retrospect, it was obvious. I should separate out the soft and collinear modes as opposed to mixing them together using more polynomial-based strategies.
Thank you.
May I ask a question?
Yes, of course. Go ahead, Alvaro.
Did the machine tell you the ratio of the quark to gluon and the gluon to gluon couplings?
Excellent. So for this example, no. So you're basically asking, did it figure out the ratio of the color factors? Mm-hmm. Yeah. But it didn't figure that out because we didn't ask it to. So it turns out that for quark-gluon discrimination, turns out to be a case where, at least at leading logarithmic level, the optimal observable to use is independent of this ratio. So whatever the ratio is, at least at leading logarithmic level, it doesn't matter. The same optimal classifier would be obtained. But it's a really great question to think about. What if I want to simultaneously figure out, is it a quark, is it a gluon, as well as figure out what the color factors are? And that would be something that you need to encode that into the loss function. You need to have something in the loss function where you actually have training data that has different of these color factors, and then actually say, I want to do a simultaneous optimization of the ability to tell the difference between quarks and gluons, as well as determine with error bars what the Casimir factors are. But this is something that we've thought of. I don't have any good answers to it, but that would be very cool to have the machine have to do a secondary task that might actually teach us something about the underlying physics.
We'll ask again in 1 year when you've done it.
Thanks. we will see. It turns out that this problem is relevant because what you really often care about is color singlet objects. So the ability to figure out whether something's a color singlet would be very, very cool. And so understanding this Casimir from that perspective, basically understanding when it's zero, is something that I'd like to know. Okay. In particular for understanding boosted Higgs bosons.
I don't see any other questions. Then we can come to the third part.
Okay, excellent. Okay, so the last part here is when are collider events similar? And let me just say at the outset, this is a type of question that we don't ask often in collider physics. We are very used to taking collider data, and we use that master formula that I showed you before. We calculate a cross-section. And how do we compare theory cross-sections to experimental ones? We make histograms. So we don't really ask the question, when are collider events similar? We just say, here's a collider event, what's its property? Drop it in a histogram. So this notion of understanding when things are similar, we learn this from the machine learning literature or the artificial intelligence literature that deals with unsupervised strategies. And so this is not going to be anything to do with neural networks, but this is an example of an unsupervised learning strategy that allows us to answer this question and make interesting connections to theory along the way. Okay, so I showed you one collider event before. Now let me show you two collider events. So this is two collections of points in momentum space. And one is from the CMS experiment, one's from the Atlas experiment. And you'd like to know how close are these collider events to each other? And I should say it's not obvious that this question is interesting. Hopefully I'll convince you by the end of this section that it is interesting. But it's also not clear what I mean by closeness. I mean, one was taken at CMS, the other as Atlas. And so if I wanted to talk about spatial separation, I could say that these are 8.5 kilometers apart. But that's like a kind of a stupid notion of closeness. Here, we should say that these events are close because they actually have similar topologies. If you ignore the fact that Atlas and CMS have chosen different color schemes for their detectors, you see that you have this multi-jet final state on the left, multi-jet final state on the right. There's some similarities, especially if you take the Atlas one and twist it a little bit, like where the jets are kind of align with where the CMS jets are. How would you give a number to this closeness first? And then what would you do with that number afterwards? That's second. And it turns out that there's a whole literature that deals with this if you focus on energy flow. So this is actually a hard question to answer if you don't take the energy flow concept seriously. But if you take this energy flow concept seriously, then talking about the similarity of these events is actually related to a very cool part of the machine learning AI literature. So I want to talk about the similarity of two energy flows. So just to remind you, this is talking about things in terms of energy density. And here I have a red jet and a blue jet. And I want to know how similar is the red jet to the blue jet. Okay. And so crossing my fingers that the animation works this time. It's like 50-50 shot on whether the animation shows up. So let's see if it works. So I want to talk about the similarity of these two energy flows by trying to distort one energy flow into the other and talk about how difficult that distortion is. So I want to distort. Oh, it's not distorting. Well, it's distorting with very low frame rate. So I'm going to make the red jet distorted into the black, the blue jet, and then go back and forth. And I have another animation in a moment that might show up better. But this is an example of what's called an optimal transport problem. And the distance has different names that you infer from this. The Earth mover's distance, or the one Wasserstein metric. And this is a way of comparing distributions of anything. Here it's distributions of energy as seen on my detector. And I can compare the similarity of distributions by talking about how difficult it is to rearrange one pattern into the other. So let me say a little bit more about this Earth mover's distance. So we learned about this from the computer graphics community. It's an example of an optimal transport problem. Has a history actually going back to the 1780s with a French mathematician, Monge, who wanted to talk about the transportation of dirt and how to do that in the most efficient way. And apparently in French, there's a different word for a mound of dirt, which is déblai, and trenches to put the dirt, that's called remblai. And so the study in the 1780s was, what's the optimal way of moving the déblai to the remblai? This shows up in the mathematics literature under the name of the Wasserstein metric, which is the minimum work, stuff times distance needed to make one distribution look like another. And you can imagine why this might be relevant in image processing applications. You want to say, are two images similar? Well, how much do I have to move the pixels around to make one image look like the other? But anytime you have a notion of an additive weight, in our case, that's going to be energy, and a ground distance, that's going to be angle on the detector cylinder, then you can turn that into a distance between distributions. And I suspect many of you have thought about data sets that are of the form of distributions. And one way of comparing distributions is what I said earlier on with this KL divergence, but this Earth movers distance is another way of talking about the distance between distributions or their similarity, where 0 EMD corresponds to the distributions being identical. We took this idea of Earth movers distance and brought it into particle physics under the name of the energy movers distance, because what we're doing, we're moving energy around. And these are the same two jets as shown before, the red and the blue, where I'm distorting one to the other, and the amount of distortion of moving the energy from one place to the other is shown as these black lines. And the optimal transportation plan between these energy flows, the cheapest way of moving the energy from one configuration to another, which involves the cost to move energy, as well as a penalty term if I have two jets that have unequal energy. Basically, I need to make more dirt to move around. This together has the fascinating property of defining a metric on the space of events. So again, I have these blue jet. That blue jet, I can think of abstractly as a single point in an abstract space. Sorry, what did I say? Blue, the red jet, the other one, I can do the same thing and make it be an abstract point in this space. And the flow of making the red look like the blue turns into a distance in this abstract space. And I have a metric that's induced on this space, not a metric in the GR sense, so not something that's a differentiable manifold, but a metric in terms of pairwise distances that satisfy the triangle inequality. And I can use all the various pairwise distances to triangulate out my data set. And that's a useful thing that I can do once I have a notion of distance, is I can now start to use a geometric language of similarity of events for my data analysis. So let me show you what this looks like. Hopefully this movie is going to show up a little bit better. So here we now have three, I think it's still stuttering. We have three jets, the red jet, the green jet, and the blue jet. And I'm distorting one into the other. So let me actually just show you this. I think it plays better if I just show it in my screen here. So yeah, that like, it seems like it's going smoother. So I'm distorting the red jet into the green jet into the blue jet, and the blue jet back into the red jet. And the video that's in the center of that triangle is showing you the transportation plan. And in some sense, the difficulty of that transportation plan gives me a notion of distance. It has units of GeV. And from these various distances, I can like build what an MIT news reporter called a social network of jets, basically looking at the pairwise distances between all these various jets and using that to create a triangulated graph-like structure that tells me about the relationship of events to each other. So that's a pretty cool thing. And it unlocks a different way of us thinking from a theoretical perspective about our collider data. Since instead of talking about observables, things that I measure and calculate cross-sections with, now I can start to think about new types of geometric objects, about what is this induced space that I've triangulated. Okay, so to show you some examples in my remaining time, let me show you some things that are, I think, new to collider physics, or at least a new language to talk about it. So I have this induced space induced by this energy mover's distance. And when you have a space, you could ask something very natural, which is, what is the dimensionality of your space? But we're doing this in the context of machine learning. Machine learning at a kind of broad level is functions that are defined by data sets. And so if I have a data set and I compute all these pairwise distances and triangulate the space, I need to use that data set to infer something about the dimensionality of that space. So I need to machine learn in the sense of using my data to define this quantity, and different data sets would give me different estimates of what that quantity would be. And I would only get the true dimension in the limit of having infinite sampling of my space. So if someone gives you a sampling of dots and you want to figure out its dimensionality, what do? Well, you take those dots and you ask, as I change my my radius or distance away from me, how many neighbors do I have? How does the growth of my neighbors scale with my distance? And so here, if I look at the spiral, and if I zoom into this well, if I zoom way in, just like we have for social distancing, where we're 2 meters apart from each other, here the dimensionality is 0. I'm a point and I don't get any more neighbors as I change my scale. But if I zoom out further and I see this collection of dots here, I say, well, actually, the number of neighbors that I have grows quadratically. Therefore, this is a 2-dimensional intrinsic dimension, is what we would call it. If I zoom out further, I see that actually those dots are aligned along a line. And so this actually talks about the dimensionality turning into 1 when I'm at this larger distance scale. And eventually, as I zoom out, I have a more space-filling spiral. And eventually, if I zoom way out, I have just a dot again. So we can do the same thing with the space of jets. I can take a collection of data, and I can take that collection of data, and I can say, as I zoom out in energy scale, or the similarity as induced by this EMD, how does the dimensionality change? And let's start off with a QCD calculation. So this is a different type of QCD calculation. This is not computing a cross-section. This is computing, from first principles, the dimensionality of the induced space of jets as induced by this energy mover's distance. So something that's a little bit hard to put in your head a bit, but we did the theoretical calculation to leading logarithmic accuracy. And actually the dimensionality depends on the Casimir factor. And in fact, this dimensionality could in principle be used to extract whether you had quark versus gluon enriched jet sample. And this dimensionality shares some features of like an anomalous dimension in QCD. That is, we have a dimensionality that's proportional to the strong coupling constant, proportional to the Casimir, has a logarithmic scaling with energy scale. And it's a very intuitive picture. At very high energies, essentially we can only see a single quark or gluon. And therefore, a quark or gluon is just a dot, and therefore it has dimensionality 0. And then as I go down to lower energy scales, I start seeing the parton shower. I start seeing the growth in dimensionality coming from the fact that I have more and more and more splittings, and the phase space now opens for me to see more structure. And it's kind of cool that the dimensionality, again, is proportional to this Casimir, and cool to see that if I take 500 or 400 GeV jets and I analyze them at a length scale of like 10 GeV, we have a dimensionality that's like 4, 5, 6, something like that. And I cannot just do a theory calculation. I can do a calculation using this open data, which is a mixture of quarks and gluons. And here is using open data, this dimensionality, where you can see excellent agreement between open data in black and Pythia simulation in orange for what that dimensionality is. And this is exposing an aspect of the kind of fractal self-similar renormalization group evolution of jets. But from a machine learning or data science perspective, where I'm using the data, letting the data determine my notion of dimensionality, again, by this intrinsic dimension formula. So that's something cool that we can do. Something else we can do is we can talk about trying to visualize the space as a whole. So I have this 4 or 5 dimensional space. I can try to project it onto a slide for you. So project it onto 2 dimensions and try to make a picture of it. And that's, as you might expect, very hard. So think about this gray blob as if it were like a density plot of jets in this projected space. So this gray blob, you should be thinking about this as corresponding to, I think in this case, 30,000 jets that are sprinkled here, where the darkness of the gray blob tells you how many jets that you have there. And this 2-dimensional projection has been done in a method called T-distributed stochastic neighbor embedding, which preserves the distances as best as you can of this high dimensional space, such that when I project things down, the Euclidean distance in this space is close to the EMD that I computed before. Now, this 30,000 jets are hard to visualize, but we can take example jets. And here I'm selecting the 25 most representative jets, the jets that actually, in a statistical sense, are the best representatives of the 30,000 as a whole. And I'm showing them here, where the size of the circle tells you basically how many jets that one image is being a proxy for. So the larger size means that there's a lot of jets that look like this one, a lot of jets that look like this one, fewer that look like this one that's smaller. And what's cool is that this is a purely machine learned representation. I haven't given it any theory behind it. And yet it's discovered for itself that, at least if I project down to 2 dimensions, that this Altarelli-Parisi splitting function that I showed you before, where the dynamics of the jet are governed by the collinear structure, which is the opening angle of the jet, and this energy sharing Z variable is basically saying how much energy is carried by a gluon in the radiation process. You can see that if I go from over here, I have collimated jets. Over here, I see wider opening angle between the jets that I see. And then for energy sharing, if I'm down here, they're asymmetric energy sharing. If I'm up here, it's more symmetric energy sharing. So the machine, in some sense, has learned for itself, oh yes, if I want to try to capture distances via this EMD, and I want to capture them in 2D, the best way to do it is to essentially use the same coordinate system that we would have done for doing DGLAP evolution. And so again, this is kind of a cool new tool imported from the statistics world that ends up connecting to QCD in an interesting way. Then you can start asking questions where can I do an even better job with these techniques than I could do before. So for example, a question was asked about traditional jet processing techniques. And here's an example of a traditional jet processing technique that I developed called n-subgetinous. This is a ubiquitous jet substructure observable used for almost a decade now, used for identifying boosted top quarks that have this characteristic three-pronged structure. And when I first introduced this formula, I knew that this formula was based on QCD literature. It's based on work by my colleagues Ian Stewart, Frank Tackman, and Walter Wallerwein on n-jettiness, based on work going back to the 1970s on similar types of prong-like tests. But people were saying, geez, this formula looks really ugly. You have to take a minimum over various angles. There are angles to some axes with an energy weighting, and those axes you vary until you try to minimize a quantity. And it seemed like kind of an artificial formula. It's a formula that made sense from the singularity structure of QCD. This turns out to be one that captures in a very nice way the collinear singularities of multi-pronged jets. But it seemed kind of artificial and ad hoc. And you could say, now that I have this EMD concept, maybe there's a cleaner way, a better replacement for n-subgetinous, a better way of characterizing the prong-like structure of jets by using something inspired by this EMD picture. And to our both delight and dismay, there is a way of using this EMD to capture the prong-like behavior of jets, which turns out to be identical to n-subgetinous. And we didn't know this, but I can take this long formula, I can shrink it down. And here is, in some sense, a nice intuitive way of thinking about what n-subgetinous is trying to do. So I have my jet, let's say, has 20, 30 particles in it. And I want to know, to what extent are those 20, 30 particles, this red spray of radiation, to what extent is that well represented as if it had only 3 particles? This P3 is the manifold of all 3 particle configurations. Why can I talk about a manifold? Well, because I've determined this metric, so I can talk about spaces. And one subspace that I can consider is the subspace of all possible 3 particle configurations. And the distance between my jet and the closest 3 particle configuration, that distance as measured by the EMD, basically like the impact parameter between my jet and this manifold, that is what we defined previously in terms of n-subgetinous. And this minimum here is a minimum over a manifold that mimics the minimum that appeared over here in n-subgetinous. And in fact, many optimization problems that appear in particle physics have this flavor, and you can actually convert them from an observable to a distance between a point and a manifold, which gives us a new geometric perspective on things. And it turns out that it's not just n-subgetinous. It turns out that 6 decades of collider physics we've been able to translate into a new geometric language, including the very definition of infrared and collinear safety itself turns out to be much easier to state in this EMD language. Event shapes like thrust that I mentioned before, jet algorithms, jet substructure techniques, as I just mentioned, even pilot mitigation schemes have taken that form. I see them kind of running low on time, but let me just very quickly give you an example relevant for new physics searches. So it turns out that thrust can be viewed as the distance between an event and all possible back-to-back 2 particle configurations. And so this distance between this point and a manifold of all possible back-to-back configurations, that is what thrust is. And here's a plot of thrust from the 1990s. And it turns out that we were doing optimal transport problems, even though we didn't know it when we were doing thrust measurements. But let's say you're thinking about some new physics scenario, and your new physics scenario doesn't generate jet-like configurations. Let's say it's some hidden valley scenario that generates quasi-uniform event configurations. Well, then instead of talking about the distance to two particle configurations, you can talk about the distance to uniformity. And this is work that I did with Carrie Cicerotti, who's a grad student at Harvard. And this distance to uniformity is easy to define in terms of the EMD. You just do it. You just say, hey, this notion of isotropy is just how close is your event to this uniform configuration. And this observable turns out to have a really nice dynamic range when it comes to separating out different degrees of isotropy. And you can actually tease out complicated new physics scenarios via this observable that would have been otherwise difficult to see using more traditional thrust-like measurements. Okay, so that's what I wanted to say about when events are similar. They're similar, at least as far as this energy flow perspective. They're similar when they have this small energy mover's distance. And then once we have this EMD concept, this inspires new geometric data analysis strategies for approaching collider data. Okay, so let me take a pause here, and then I'll just have 3 slides in conclusion after this. But let me see if there's any questions about this EMD work.
I do have a question.
Yes,
Yes.
Alvaro, please.
Has the machine taught you anything about missing energy events?
Excellent. So this is something that I'm actually working on currently with a student, and we've thought about which strategy would be useful here. And one of the things that we're trying to figure out is whether the machine can do a better job of understanding missing energy configurations than traditional strategies based on just missing transverse momentum. And I think you have to think about, like, is there additional information that I can exploit that can help me tease out missing energy? And we have some hints of things which I'm not comfortable saying because I'm worried that they may not be true. But one of the things that we're trying to figure out is we're trying to figure out the correlation in a information theory language, the mutual information that you have between missing energy signatures and other information in the event, such that I could actually do a better job of inferring the amount of missing energy or the direction of the missing energy by using other information in the event. The reason why I'm skeptical about this working is that machine learning is only as good as the training data. And if your training data is biased in some way about the relationship between missing energy and visible energy, then that bias is just going to be translated directly into your inference. And so garbage in, garbage out. And so one of the questions that we're wrestling with is, how would you be able to figure out in a data-driven way whether or not your machine learning was biased? And I don't yet have a good answer to that. But yes, this is something that would be very cool if you could actually do better jobs for dark matter searches by using this machine learning strategy.
You can erase a particle that you have actually seen.
Yes, absolutely. So for example, if you want to look at a proxy for backgrounds involving neutrinos plus jets, you can look at zeta to mu mu, delete the muons. And you can do that, absolutely. And then the question is the signal that you're looking at, is it the same as removing particles? And the answer is both yes and no. Yes, that's part of what's going on, is that you just don't see particles. But another thing that's going on is that there's a mismatch, because there's not just missing momentum, there's also missing mass from dark matter. And therefore you have actually a different scale, a different root S hat of the collision. And you have to ask if that difference in root S hat in terms of parton distribution functions and things like that, if you can correct for that change from just doing particle deletion studies with events that you've seen. But yes, absolutely, that would certainly be a tool that you'd want to use for estimating missing energy impact. Yeah.
Thanks.
Any other question right now? I would have one, but since we are indeed running a bit late, I may save it for afterwards if some time is left. Go ahead, and then
my summary is just quite simple. So hopefully I've given you some sense of the way that you can gain new insights into particle physics facilitated by these advances in machine learning. And hopefully I've given you some sense that it's like a bigger world. It's not just black boxes and machines trying to think on our behalf. It's really a toolkit from mathematics, statistics, and computer science that we can bring in. I've told you about 2 examples from my work. There's a whole literature out there. Other examples from my work that I'm happy to talk about is understanding jet quenching via optimal transport, understanding the definitions of jets using things like blind source separation, or also techniques in topic modeling are relevant for this, which I can talk about. Using just graph theory turns out to be interesting for understanding scattering amplitude structures as well as effective field theories. And this is, again, incorporating tools from the broader community into the physics world. One last shameless plug for our institute, the Institute for Artificial Intelligence and Fundamental Interactions. I told you about what we were doing from my work on the particle collider side, but we also have things in gravitational waves, ab initio nuclear physics calculations, astrophysics, mathematical physics, dark matter studies, and more. Again, the slogan is machine learning that incorporates first principles, best practices, and domain knowledge from fundamental physics. And so hopefully, for those of you who aren't doing this, might inspire you to enter into this. And as Sven said, put it in your next funding proposal. And let me just leave you with the summary slide that I tried to tell you that machine learning offers powerful tools to analyze collision debris, and we're making progress towards this fusion of deep learning and kind of deep thinking. What is a collider event? Well, from a machine learning perspective, it's an unordered set of particles describing the energy flow of jets, and this inspires these network architectures that are designed for encoding symmetries and infrared and collinear safety. And then finally, when are collider events similar? When their energy flows are similar. And this inspires these unsupervised learning strategies based on the event geometry, which have been relevant for the past 6 decades of collider phenomenology, even though we didn't know it. We have a new language to talk about a variety of things that I've given you some hints about in this talk. And we'll see if the next 6 decades also benefits from these new toolkits brought in by the machine learning world. Okay, thanks very much, and looking forward to more questions.
Thanks a lot for this interesting talk. Really nice overview. I see that Alvaro is still unmuted. You want to ask another question?
I wouldn't mind asking a question.
Yes, go ahead.
The last 2 questions that you have in this transparency, would you answer them for gravitational waves?
That's a fantastic question. So I've thought about.
All of mine are.
yeah. So what is a gravitational wave event? Of course, it's a waveform, but kind of what is it intrinsically? And one way of answering that is to ask, when are 2 gravitational events similar? So clearly, if they happen at different times, that does not correspond to a notion of dissimilarity that we care about. So, we want to kind of set t equals 0 to be, let's say the start of ring down or something like that. And so you want to allow yourself to time translate waveforms when you're trying to capture a notion of similarity. But naive notions of similarity don't capture what we want. So let's say I have an inspiraling binary, and I change something about the relative masses of the inputs by a little bit. Well, when I do that, of course, I can change the various frequencies. And if I do a kind of standard KL divergence to test for similarity, the KL divergence could be small, but for a stupid reason that basically I've taken my waveform and kind of stretched it by a little bit. And somehow you want to have a notion of similarity where the notion of similarity captures the notion of similarity of the binary inspirals themselves. In the quark and gluon context, quark jets are closer to themselves than they are to gluon jets. Gluon jets are closer to themselves than they are to quark jets. There's a notion of similarity induced by the EMD that's kind of preserves our notion of when kind of categories are similar. You'd like to do that in the same way for the gravitational wave case. You'd like to be able to say, hey, if I see 2 gravitational wave events that are similar, they're similar in terms of the underlying physics parameters. And so that would be a very interesting thing to think about, is like, how do I want to allow myself to distort or compare gravitational wave things such that small changes to the underlying parameters lead to small changes in whatever that distance is. So I don't know what it is, but fundamentally, my guess is that gravitational wave signals are just time series data. And how do you say whether 2 time series data are the same? Well, it depends on what your series is of, and probably analyzing things in temporal space is probably not the right way of doing it. Probably you want to look at it in Fourier space. That's probably a better space to be comparing similarity. But this would be a very cool thing to figure out, and hopefully it matches on to the theory calculation of the way that you actually make predictions of gravitational wave signatures.
Thank you. I will mute myself.
Maybe I can make a comment here, and then still, if nobody else has a question, ask my question. We had a talk yesterday in our Christmas workshop about gravitational waves and more from the theoretical side. And among other things, shortly discussed was this one event which seems to come from the forbidden zone of black holes. And what I learned, that there is at least one analysis or one paper out that says, well, there's a second solution, a second solution that would give you a similar form and actually has masses of the black holes that are not in the forbidden zone. And so this would be kind of the opposite. Yeah, could one try to find differences in the two patterns that would then tell us what which one is more probable than the other?
Right, but I like that word that you add. Which one is more probable than the other?
Yeah.
And fundamentally, all of this work that I'm talking about is in the context of probability and statistics.
Yes, yeah.
And you can never say anything with any certainty if you just see a finite number of samples.
Yes.
And so what you're really asking about is it more likely or not more likely? And there are trade-offs, and all the things that I glossed over here about, like, what exact loss function do you use, or what functional parameterization do you use? Those choices end up affecting what we might call our theory priors, that certain things are easier to learn versus harder to learn. And the one that machine learning ends up finding is influenced by your prior knowledge about things, and changing the priors can change the interpretation. And so if you had a very, very strong prior that you shouldn't be able to be in this forbidden zone, then it's both a good and a bad thing. It's a good thing that you're putting your theory knowledge in, but a bad thing if you're actually missing a discovery. And that's something that I'm very worried about, I'm worried about, okay, how can I design machine learning strategies that, if there's a surprising thing that happens, doesn't sweep it under the rug? If I'm trying to do quark-gluon discrimination and I get something that has nothing to do with a quark or a gluon, will it alert me to the fact that, hey, this looks weird? How do you encode that surprise into a loss function in a way that a physicist could interpret?
Okay, one more practical question. You were mentioning pileup, I think on page 52 as one of the examples. Just the outcome of this. Do you think that with your techniques, you really have pileup better under control, or by how much better, or what was the result?
Yeah, good. So there's two different things. So one is saying that this is saying the past 6 decades are expressible in this new geometric language. So for pileup, it turns out that pileup can be interpreted as following a geodesic in this abstract space, where I'm at a point, I have the uniform configuration, and I'm following the geodesic not towards the uniform configuration, but away. And I move away a certain number of steps from that uniform configuration. And so that's a geometric way of talking about what pileup strategies are doing. And the way that we currently do pileup is with approximations of this. And you can do this thing directly. And when you do this thing directly, what you realize is that pileup mitigation is not just about removing uniform radiation. So we did this and we get good performance, but no better than traditional techniques. What you really want to do is you want to account for your knowledge that pileup has fluctuations, and try to use that knowledge of what those fluctuations are from, let's say, minimum bias events, and encode that fluctuation knowledge into your pileup mitigation. So this is an example where we could translate something into a new language. We say, great, it works just as well as the old stuff. It's just in a fancier, smoother, cleaner language, easier to explain. But then having done this highlights something that you hadn't thought of before, highlights the important role of fluctuations. And I'll say this again, also in the context of this isotropy work, that Carrie and I were very pleased to see this plot and the separation between kind of different new physics signals. But then it emphasized to us, oh wait, the question actually isn't just uniformity. There's a difference between uniformity in angle and uniformity of an energy. And actually, if you're trying to think about like what type of new physics strong coupling scenario do I have, it's not just about one or the other, and you somehow need to incorporate both. And it kind of opens your eyes to thinking about, okay, what is the way of measuring the thing that I really care about? Or in this case, once I figured out whether it's isotropic or not, kind of the degree of fluctuations, kind of like, going beyond just saying the CMB is uniform and really trying to study in a detailed way what the fluctuation patterns are. So anyway, for pileup mitigation, the answer is that our method does just as well, but it makes it easier to see what the next stage of evolution needs to be in that context.
Okay, thanks a lot. I don't see any other hands raised. Then, Jesse, thanks a lot for this
Thanks, man.
interesting talk. Thanks for giving us the opportunity to listen. And we close this here, the session. We have a coffee break for about 9 minutes, and then we continue with the Netta. I'm not sure who's actually the next host. I'm pretty sure it's not me, but